my side. I don't wanna waste what's left. The storms we chase are leading us, and love is all we'll ever trust. Yeah, no, I don't wanna waste what's left.
Okay, guys, in my part, we will be finding the multiplicative inverse of an element 17 in Z20. So firstly, before I start, I want to state theorem 2.30, which states that an element A in Zn will have a multiplicative inverse in Zn if and only if A and N are relatively prime. We know that relative prime numbers are those that have the greatest common divisor, which is 1. Then from there, we continue with our solution. We'll start by using the Euclidean algorithm. So using the Euclidean algorithm, we'll say 20 is equals to 17 into a quotient plus a remainder. So we said how many times does 17 goes into 20, and we find that 17 goes only once into 20, and it leaves the remainder of 3. Then we move forward again. Say 17 is equals to 3 into a quotient plus a remainder. So how many times does 3 goes into 17? That will be 5 times, and it leaves a remainder of 2. Then again, we say 3 is equals to 2 into how many times does 2 goes into 3? That is once, plus a remainder, which is 1. Then again, moving forward, you say 2 is equals to 1 into a quotient, and say how many times does 1 goes into 2? And that will be twice, and it leaves a remainder of 0. So this last equation here basically tells us that 1 here is our greatest common divisor of 17 and 20, and it actually satisfies theorem 2.30. Then we move forward. We'll be solving for the non-zero remainders. Solving for the non-zero remainders, we mean that we'll be basically making the non-zero remainders subjects of each equation above. So the first equation will look like this. It will be 3 is equals to 20 into 1 plus 17 into negative 1. Then the second equation will be 2 is equals to 17 into 1 plus 3 into negative 5. Then again, the last one, it will be 1 is equals to 3 into 1 plus 2 into negative 1. Then moving from here, we'll be substituting the remainders 3 and 2 into this last equation here. So where there is 2, we'll put in 17 into 1 plus 3 into negative 5, and where there is 3, we'll put in 20 into 1 plus 17 into negative 1. Then, but we'll do this orderly, so to avoid confusion. So we'll start by substituting in 2 here. Then it will be 1 is equals to 3 into 1 plus, where there is 2, we have substituted 17 into 1 plus 3 into negative 5, and we have now introduced the square bracket to avoid confusion into negative 1. Then from here we simplify this, and when we simplify this, this is what you get here. We get 1 is equals to 3 into 6 plus 17 into negative 1. Then from there you substitute in 3. So where there is 3, we put in 20 into 1 plus 17 into negative 1. And this is what you get. Then from here you simplify this equation here. Simplifying this equation, this is what you'll get. You'll get 1 is equals to 20 into 6 plus 17 into negative 7. So from here we can actually conclude that 17 into negative 7 is congruent to 1 mod 20, and we see that negative 7 here is our inverse. But since 17 is positive, we need to make negative 7 positive. And how do we do that? We just add 20 to negative 7 and we get 13. So 13 will be our inverse of 17, and that is our final answer. Thank you.
And on we'll go, through the wastelands, through the highways, till my shadow.
Okay. I have to find the solution of a congruent class of 6 times congruent class of x is equal to congruent class of 4 index 8 whenever there is a possible solution. So firstly we have to write this equation in a form of a linear congruence. So we're going to have 6x is congruent to 4 mod 8. This equation has a solution if and only if a greatest common divisor 6 and 8 divides 4. Such that greatest common divisor of A and N divides B is 6 and 8 is equal to 2, which divides 4. So this equation has two solutions. So firstly, we have to divide by 2 on both sides of this equation. So by dividing by 2, we find 3x is congruent to 2 mod 4, and the greatest common divisor is 3 and 4 equal to 1. So from this equation, by expansion, we start by adding 2 and keep on adding 4 until we get a multiple of 3. By doing so, we got 3x is congruent to 6 mod 4. Since 6 is a multiple of 3, then we divide by 3 on both sides. So by dividing by 3, we get x is congruent to 2 mod 4. So the first solution is then x is congruent to 2 mod 4. So and since there are two solutions, the second solution is 2 plus 4 mod 4. As we said, we keep on adding until we get a multiple of 6. So 2 plus 4 is equal to 6. So x is congruent to 6 mod 4. So that is our second solution. So therefore, a congruent class of x is equal to congruent class of 2, or congruent class of x is equal to congruent class of 6.
And on we'll go, through the wastelands, through the highways, and on.
Guys, so today I'm going to present a problem from exercise 3.4 from assignment 2. In cyclic groups, there is a theorem that says that every subgroup of a cyclic group is cyclic. So I'm required to prove that theorem. So to start with the proof, we first let G be a cyclic group, which means that G has a generator. So we let A be the generator of G, which also means that every element of G is a power of A. So we can write the entire group as the set containing integer powers of A, given by this notation. We then let H be a subgroup of G. Remember, our goal is to show that H is cyclic. If H is generated by E, meaning that it is trivially cyclic, then we can conclude that H is cyclic, and this completes our proof. But if H is not trivially cyclic, then we let B be an element of H, where B is equals to A to the M, since B is also an element of G and all the elements of G can be generated by A, and where M be the least positive integer. Remember, we need to show that H can be generated by A to the M or B. So the strategy here is to prove that any random element of H can be generated by B or is equals to a power of B. We then take any H in the element of a subgroup H, so we can write H as A to the N for some integer N. Then, by applying the division algorithm for integers M and N, there exist unique integers Q and R such that N is given by M, Q plus R, where Q is the quotient and R is the remainder, with R being greater or equals to 0 and less than M. Then we can rewrite this as A to the N is equals to A to the M times Q plus R. Then, by applying the laws of exponents, we can rewrite this as A to the N is equals to A to the M to the qth power times A to the R, which is our equation 1. Then, since H is a subgroup, this means that H is also a group, and every element in the group has an inverse. So we are going to look for the inverse of A to the M to the power of Q and multiply it on both sides of the equation, as we did here in this equation below. So we are going to multiply by the inverse of this on both sides of the equation to obtain A to the M to the negative Q times A to the N is equal to A to the R. And remember from the previous slides, A to the M is an element of H, meaning any power of this element is also an element of H. And also, A to the N is the element of H, meaning the whole product here is also an element of H. And also remember that A to the M to the minus Q times A to the N is equal to A to the R, meaning if this whole thing is an element of H, also A to the R is also an element of H. And by the choice of M, we obtain that R is equal to 0. Remember, M is the smallest positive integer, so R cannot be greater than M, so our R has to be 0. Then by substituting R in equation 1 above, we obtain this equation. We have A to the N is equal to A to the M to the Q to the qth power times A to the power of 0. And we know that in groups, any element raised to a power of 0 is equal to the identity element. So we obtain this equation. So we have A to the N is equal to A to the M to the power of Q. Then remember, A to the M was equals to 0. So we substitute back our was equals to B, sorry about that. So we substitute B back into the equation. So we have A to the N is equals to B to the Q. And since A is generated by a power of B, this means that B is a generator of H. Hence, H can be written using this notation, which means that H is generated by B. So, as you can see that our aim of this proof has been completed. Therefore, H is cyclic, and this completes the proof. Thank you for this opportunity.
In this video, I'm going to present a problem from the last assignment, which is based on section 3.4. The question says that I must prove that G is an abelian group. Given the fact that you let G be a group such that A squared is equal to E for each A is an element of G. So basically what I'm going to do in this video, I'm going to prove that G is commutative, so I can simply just conclude that G is an abelian group. So I'll start by assuming that G is a group and A and B are arbitrary elements of G, meaning A and B are elements of G. And we also have A squared is equal to E and B squared is equal to E. Since we know that G is a group, therefore A times B is an element of G. So that implies that AB all squared is equal to E. Okay. We know that AB all squared is equal to E, but AB all squared can also be written in this form using our exponentials law. We also have A squared is equal to E and B squared is equal to E. Therefore, we continue from where we ended, like this. But in this case, we can simply change this manner like this using our associative law. We simply just grouped B and A like this and let this A be in the side and let B be in the side. Moving forward, E can also be written like this. So we can simply just say E is equal to E times E, but these E's can be replaced by A squared and B squared. Reason being is that they both equals to E, so it would be now be in this form. The reason is that they both equals to E, but A squared and B squared can be changed like this. Reason being is that we used our exponentials law. And also we can change this form into this manner using our associative law, which simply just grouped A and B like this and let A be in this side and B be in this side. If you look at these expressions, this one and this one, they both equals to E, as you can see, so we can simply just equate them. So it follows that A into BA close brackets B is equal to A open brackets AB close brackets B, since they both equals to E. Both equals to E. Therefore we have this. Okay, we can simply just divide by A in this case, then we get this, and we also divide by B, we get this. As you can see, we derived this equation by simply using our cancellation law. So basically it follows that BA is equal to AB for all choices of A and B and G. So we simply just proved that G is commutative, so we can just conclude that G is an abelian group since it is commutative.
To our lecturer, Dr. Krishnannair, and to my fellow classmates, I greet you all. My name is Tabiso Cyril Mteto. I am the leader in Group 3. I'll be sharing a presentation that is based on the groups, which is 3.4. Now let X and Y be elements in a group G such that X, Y are elements of a center of a group. Now we are required to prove that xy is equals to yx. Firstly, I will define the center of a group. Now the center of a group G is the set of elements that commute with every element of G. Now it is denoted by Z in bracket G. Now since we are required to prove that xy is equals to yz, now we will multiply by x this side and by x on this side. Since this is the equation, what we apply on this side, we have to apply it on this side as well. Then we'll be having now x times in bracket xy equals to x times in bracket yx, and then I will divide by the x that is next to xy, both sides, such that I will be now having x equals to the inverse of x times by x times by yx. Now let us look at the proof. Okay, now since now xy is equals to the inverse of x times by x in bracket xy, close bracket, and xy is an element of a center of a group, now we can say we have xy equals to the inverse of x times by x in bracket xy. Due to the fact that the multiplication is commutative, then I can say xy is equals to the inverse of x times by in bracket xy in close bracket times by x. Now the multiplication is commutative. Now since the multiplication is also associative, so we can say we have xy equals to, so now we have grouped the inverse of x and this x that is next to y. Then we have xy equals to the inverse of x times by x, all in bracket times by yx, because the aim here is to make the right hand side to be yx. Then now we have a multiplication is associative. Then now we have xy equals to yx. I thank you.